Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we're going to get back into real analysis today. So we did 3 problems last stream, so I thought we would try to do some more. The amount of problems I have... Oh, hold on a minute. I actually have to get my problem sheet. Sorry about that, guys. I forgot that my notebook was not in the room where I stream in, so I had to quickly fetch it. So let me find the page where I actually have the problems in. Here it is. So we have to do, so right now we did, I think 1.4, 1.6, and 1.9. So I think now we have to do 1.10. But happy Tuesday to you guys. How's your Tuesday going so far? Hopefully it's going pretty well. You're almost at Wednesday, so the halfway mark is just around the corner. Let's expand this. Okay, cool. Now, so I feel like this might have to be proof by induction, sorry. Not injection, what am I talking about? So let's see here. Well, that's funny. Maybe I have to refresh. Hello, Major Finger. What's the best part of your day so far? Let's just write scratch work. Because I feel like... Because it says for every natural number, so... For some reason I get a feeling this might be proof by induction. I think. So, I guess... maybe... proof by induction. I also want to make sure that I have ChatGPT with us, so that way that's a big maybe. So let's see how this would work. So if we just took actually I should have wrote this and then you think it's by induction, just write out the steps, like the base case, induction, hypothesis, and stuff. I feel like math, I always stumble onto proofs instead of planning them through. Yeah. Thanks for the tip. Appreciate it. And if you guys ever feel like that I'm just struggling, just give me like partial hints. Just give me partial hints. Because I know you guys are also watching my journey, trying to understand these problems. And if not, then I'll just rely on ChatGPT to basically like kind of help me along in that as well. That's why I put it up. So we have this. So we did like from 2. And I mean, if we do it this way, then that means... Which is, yep, that's okay. So I mean that basically, so we proved from 1 to 2, and now we have to prove the base case where it's like, because like the actual case is that if we have k equals 1, then that's what we have. Now we have to actually prove the other, which is k plus 1, k power 1. Oh, oops. Forgot to put the sigma sign. So k plus 1. No, I'm actually doing this as a hobby. I'm actually trying to learn math on my own. Or like just because... Yeah, I'm basically doing it as a hobby. Because I want to learn like proofs, because I know theoretical physics, it would probably benefit to actually like know some proof writing. So I thought I would just like learn some proof writing and learn how to think mathematically, in addition to like I also do some physics problems here too, so that way it gives me practice to understand how the physical world works mathematically. And if you guys are into math and physics, or you just want a study stream to keep yourself productive, you know, consider hitting the follow. If you're watching this on Twitch, if you're watching this on YouTube Live, you know, hit the sub button and leave a comment down below, as well as hit the like button. It always keeps motivating me to keep making more streams for you guys to be better versions of yourselves within the goals that you guys set yourself on. So we'll just write it like so, and then obviously we're going to be left with the typical culprits here. Plus, and then dot 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 dot, we have and then plus k plus 1, and then k plus 1 plus 1. Okay, so, and I think we'll see a familiar pattern. So, at this rate, and this will turn into k to the second. I would expect something like combinatorics or geometry because of how they're game-like from someone learning on their own, even myself. I guess for me, it's just that I feel like, I guess I just haven't found the appeal of combinatorics yet for me. I think the thing that makes me interested in real analysis is that, well, one is purely mathematics, but also it's the backbone of calculus. So, and also like Sir Isaac Newton and Leibniz, they invented calculus like independently. So, and obviously we know Newton basically is the father of physics. So, I felt as if like real analysis can help me understand more about like physical equations than like, you know, other branches of math. Oh, thank you. I appreciate that. Okay, so let's see how this works. I mean, we do have a pattern. The thing of it is that I have to find a way to like write this so it feels like, so I can fully understand this problem here, because we're doing it by proof by induction. Because like what I've heard from like proof techniques is that if any problem involves the natural numbers, usually like when it involves like the natural numbers like causing something, like some sort of like pattern or something, like it's better to use proof by induction. And like when I first looked at this problem, I was like, I feel like this might be proof by induction, just like by intuition wise. I could be completely wrong, but I just feel as if like that might be the pattern we need here. But I could be wrong, like I said. Okay, so we have the sum. The thing is that I mean they're all fractions, so practically you would have to have them all like multiply into one another. So we would have to have them all multiply into this, so, and then we would have to put all the multiples that we multiplied up here, so therefore we would have like, let's see, we would have two, we would have like, hold on, I want to make sure that I do this right. 6, okay, cool. So 2, 3, and then like all these other numbers. So technically we would have to have a factorial of something up here. So, hey Jose, what's the best part of your day so far, my friend? In general, for results on countable sets, I'd use induction. That's just me. Yeah, that could be also true too. Because like for me, I haven't like, I know about the proof techniques, it's just that I haven't practiced looking at problems that require them. But I think it like with proof techniques, they're just good to like know. But when you look at a problem, I think you just have to ask yourself, what proof technique should you use? And I think that's basically where you just stop and think, and you're like, okay, like this proof is telling me to prove something. Is it good for direct proof? No, it seems so complicated. Can it do by contrapositive? That works, you know, like you have to basically make those decisive decisions, and that's not easy. It's just basically you stop and think, and you have to think about it for like a while. So if we did like 3, right? So then it would be 3 times 4, that would be 12. And then like 12. So this one required 3, this one required, and if it's 12, then it would require 2. So then if we have 4, then 4 times 5, that's 20. And then like 1 over 20, then basically, because I'm trying to find the actual pattern here, so it's like because 2 times 3 is 6, 6 times 2 is 12, and then, but there's no multiple here that gets us to 20, so we would have to multiply 12 and 20, or no, like something like similar to it. So I think like 60, so it would have to be 3, so yeah, you would have to multiply it, and then it would be like 1 over 60. Complex analysis this morning, numeral analysis this afternoon. Now it's time to do some... I forgot how you read that. Lebesgue? Lebesgue theory? If I'm mispronouncing that, I apologize. Like, I feel like I've heard of that though. I think I've heard of it when it was referred to like within Lagrangian or Hamiltonian mechanics. I think it's like Hamiltonian, I think. I mean, you guys are probably farther ahead in your mathematical education than I am, though. Okay, so I do feel like we do have to do a factorial in the top here, because all of these you would have to multiply by just basically getting so. I think we would have, hold on. Because I feel like there will be a factorial up here, but I just want to make sure that that's the right way of thinking, because we got a half here, but then we would have to multiply by 3 to get this. So it'd be like 3 and then 3 plus. Hold on, I think did I miswrote something? No, this, oh, okay, never mind. Let's see. So we got 3 times. One would be then what is it like being so big brain? I think like many scientists and many mathematicians would be like, no, I ain't big brain. I'm just trying to help. I'm just trying to help everybody. Because you have to multiply by 3 to get this one. And then with this relationship. So these two will give you 3. These two. But then again, you also have to do everything. Meaning that, yeah, you would have to multiply all the denominators at that point. Topology was the worst chunk of math I had to do. Why? Like, why is that the case? So I think it's like... Topology is fun. I remember like reading the definition of a topology and I was like, oh, interesting, because it doesn't, because like the way they describe it in layman's terms, it's like, oh, it tells you like how a donut is the same, I guess the same structural integrity as I know I'm not using the right words, but this is the way I would like phrase it to someone who doesn't know. It's like similar to that of a mug, a coffee mug. And like when I looked at the definition of a topology, I was like, oh, this is very, very abstract. And then like it was like nothing but sets, and I was like, interesting. I think I think with topology, it makes me a little bit excited to learn it, because like after being exposed to like, I think the way that mathematicians try to explain it to like average people that like are not immersed in mathematics, I think like learning topology like from an abstract point of view like makes me a little bit excited, even though it might be hard. It's fun until you get like some random problem that asks you to prove that some function given some property, I don't remember, it must have a fixed point. Oh, okay. Well, I guess that's the difficult part of the subject. It's just like trying to fidget away from like difficult problems. Okay, so wait, hold on. So if that is it, then that means we're given the factorial. Peanut is non-convex. Maybe I'll learn that. Maybe I'll learn that when I take topology, or try to I try to learn topology with Sascha's help. The cow is spherical. Yeah, that old physics joke, huh? Yeah, the cow is spherical. Oh, that's a reply. I was like, what does that mean, Jose? I don't know if I'm thinking about this correctly, but I feel like I am. Because you would have to like multiply all these at the bottom. Fixed point theorem. Oh, okay. Interesting. I feel like I'm on the right track. It's just that I'm trying my best to think of the pattern like in my head, because I think basically with all these, and since you have like a infinite series of them, I'm guessing they're gonna follow a pattern where it's like you have to do like hold on. I think maybe my brain is like, because technically you would have to basically do just basically get the result here. This would probably be a factorial of... Because I know the top is a factorial of something. It's just that... how do we actually prove that... how do we prove that this is equivalent to this? Because I know it has to look like this structure here. Let's see. Also, we probably have to get k plus 1 over k plus... Okay, so our end goal, I'll just write goal here so I don't forget, and I don't have to scroll back up. Our end goal is to get this. So, following the pattern, about that, I forgot to tell you the worst part. Our professor won't allow usage of anything done in class unless you develop an entire new theory. What did we cover, and well, different. That's kind of strange. I guess he just wanted you to learn like just building stuff on your own. Interesting. Maybe like to help build your intuition. But that's a pretty strict professor, though, I'm not gonna lie. Still have this. So then we would have k factorial over k plus 2. problem is that that's not that. We're on the right track. It's just that it's just getting this to be similar to this, unless we have to do, oh, maybe we have to break it down. So maybe k plus 1 plus 1. The only problem is that we have this n here. I mean, like, the n doesn't have a factorial symbol, but this one does. And I mean, going with the logic of how this is built, it feels like you have to do a factorial, like over a factorial. Unless I did something off. Hey, Rushback. What's the best part of your day so far, my friend? Yeah, because once you get to... It's almost over. Why? Was it a stressful day for you? I'll be right back, guys. Give me 1 second. Okay, we're back, guys. Sorry to keep you guys waiting. Long day, a lot of analysis today. Oh, okay. All right. I don't want to like hold out too long, so I'm going to ask our friend ChatGPT be your tutor for this part. I guess we can't do that, so I guess I'm gonna have to type it by hand. I'm working on this problem. So right now I'm just doing scratch work on it. So I'm just trying to see how the pattern unveils, because I know once we have to write the proof, we have to make it look nice. So I'm just trying to see if I'm on the right track here, because it looks like a proof by induction problem, because it deals with the natural numbers, and the way it looks, I feel like I'm getting the pattern down. Because let's see, if you're multiplying by this one, then you basically got to do the bottom here. So I guess, yeah, we're gonna have to type it by hand. Hey, Aunt Stunky. What's the best part of your day so far, my friend? Yeah, I figured it was use the induction method. Unless you guys want to give me subtle hints here, because like I feel like I'm on the right track. It's just that because this is the scratch work right now. So the thing is that I know that to get the end result here, we have to like basically like multiply all the stuff in the denominator except one of them to basically like get to this point. I was going to say just waking up again. That's fine. But I found out that I have a free night tomorrow, so that's probably gonna be the best part. Nice, that's good, that's great news. So that way you'll be able to like get the stuff that you need done or get the relaxation you need. So that is good, and Stucky, I'm so happy for you, because you work really hard on the stuff that you do. The reason why I use factorial is because like as you see the pattern right here, I know that basically in order for these to sum up, you have to basically multiply all of them by like a factor that goes into them. So, you know, like, and then it builds up on top. But yeah, maybe the factorial approach is not the right approach, maybe. Because I remember doing a lot of those problems when I was doing like, I think, sequences a lot. I do work really hard on the stuff I do. Just don't do very much. Yeah, I'm the same. But I'm thinking like basically like because here you would have to multiply like 3 by 2 and then makes it like 1. And the way the pattern is that it's like this, and I'm guessing like, you know, like you have to take like the value of n and multiply by just one, like its successor, so that way you basically end up with this on top. The bottom is fine, the one thing is the top here, because we got k here. So the thing of it is that we just need k by itself, I think, because we have n here. Unless well, n is basically the amount of stuff. So we just wanted k1 because we got k1 here. And we got I mean, maybe no. I am missing something in this part, because I mean, there might be factorial in here too, actually, because the third line? What, this part? Or are you talking about the third line here? Like from this line up here? Like the one with the K's or the one with the actual like numbers in it? Oh, the last one here. Yeah, because I feel like there's something missing, because if you were to have all the denominator basically be all the values that are basically in the denominator, like at least multiplied together. Yeah, I feel like maybe there might be a k factorial in here. These two have to multiply together. Maybe I have to erase this, because that's the thing that helps solidify the pattern. So let's erase that for a second, because let's think of the pattern. So basically 1 plus 2, that, and then 2 plus 3, 2 times 3, and basically they multiply together. And then the way this turns out is that you basically have to multiply a factor to get to this factor. I mean, to this denominator. So you have to multiply a factor to get these two denominators to match, but then you also have to multiply a factor to get these denominators to match. Induction working well here, but telescope sums are fun. I figured, yeah. Like Jose, you seem to really love to find the challenge as well as the amusement of math, and the enjoyment, I should say. Okay, I guess I'm gonna have to type it by hand for ChatGPT. Prove that. Is there a way I can type out the math without having to, like? I wonder if Wolfram will allow me to do that. So. Let's see, math input. I need math input. Nope, that's a matrix. Actually, I've never used Wolfram before, so hopefully we'll be able to all math outputs. Let's see, epsilon. Where's sigma? Excuse me. Thank you, Jose. I could just paste this in here, or do I have to paste it in Wolfram? In natural language. Understand? Okay. But thank you for that. And the rest of the question is for every natural number. Oh yeah, come to think of it, yeah, all the patterns like have like one after it, so let's just think about the last two. So at this point, we would have something like this, and then right here we would have like a big mess of stuff. So I would have to say that this would be something like this, and then I think this is not right. Because the one thing that I'm having trouble with is like, how do I actually make this pattern make sense on the bottom? Because I know it has to be like a lot of stuff multiplied together, but I don't think factorial is not going to work. What are they using the hint here? Because this one multiplies by 3 to get to here, but then this would also have to multiply by 2. Yeah, it's like, and like the rest, it seems like it's gonna, like you're gonna have to combine them. That's the one thing that kind of makes the pattern a little bit disjointed. I always forget that that is a button. I just realized why you're using k at the top of the sum. You wrote k equals 1 into k, and alright, so let's see here. You have induction hypothesis that k is equal to k. To add, put in a common denominator. this, it's just basically for me to keep track, because I know n is supposed to be very like it's supposed to be like the terms, so I just put that there just to say the k plus 1 term or the k term. That's the reason why I put it up there. It's just for me to keep track. That's why it's in the scratch work. It's not really in the proof. I know like the way I think is probably like really weird, but usually for me I understand things very visually, which is probably like not very it might not go the traditional route that I guess like most math undergrads do, because I think I don't have like the professor to tell me that I'm writing things wrong. Okay. You have the induction hypothesis and to add some term, so put the fraction over the common denominator. Multiply the numerator and the denominator of by now add oh, okay, so you can just replace everything. Okay. That's what I was missing, because I forgot that we also assumed this. So because according to this, at least in this case, it has to be like k over k plus 1, so k plus 1, and then yeah, so then you would have to do k to the second up here, which leads you to k, oh no, which leads you to Yeah, maybe you're right, but at the same time, it's like, for me, it's like, I guess it's just a mental trick for myself, that's why. I know it doesn't look like what you usually do, but like for me, it just basically just helps me like see it. It just helps me see like that I have to do the K version of that. I mean, that gives you K. Is that what we're supposed to get though? Because I thought you're supposed to get K plus 1 over K plus 2. Let's see. Okay. So we have to multiply that top. Then we're given this. That's what we did. Oh yeah, so we have to add them together. Yeah, I forgot. I forgot that part. That's what I was missing. I kind of thought I went too ahead of myself there. So. Okay, so at that point, then we're left with K plus K. Oops. Now we just have to combine stuff. So plus 2K plus 1. Is 2. Okay, now we can factor this. So K, yeah, K plus 1, K plus 1. Oops, that doesn't look like a K at all. It looks like a B. So these two cross out, and then we're left with our end result there. Cool. All right, so that's the scratch work. I mean, I don't think the proof would actually go this elaborately, do you? Okay. Proof. It's proof by induction. Like, what do you mean, Jose? Like, what am I missing? Like, I just saw your, what you typed in the chat just now. Actually, we probably don't even need this sentence here because it's saying the same thing. If you write the sum from k equals 1 to n of something, and of something that isn't related to k, you're summing a lot of 1 here in respect to k to do like right here. So like what should be on the top then? So should this just remain n then? Because I thought that was just basically the terms we're dealing with. It should be n on top, k is at the bottom. The thing inside the sum should be k and not... okay. So it should just end all the way through? Because like, like, is it always like going to be n on top? Like, even if it's like the plus, like, n, like I guess the plus k, plus 1k. At the end it should be n. Okay, no problem. Okay, because I thought you have to put the terms like what is defined here. Like, because like if you're doing for the first term, I thought it would be like like n at 1, and then like n at 2, and then n at like, you know, k or something, and then like k plus 1. I thought you had to do that for the terms like on top to identify what terms you're working with. Or is that blatantly obvious from what you're working with already? Oh yeah, for the initialize and start, and if you start at 1. So should this n be 1 then? And this n should be 2? That's the one thing, that's the thing I'm asking. Because we're just working with the two terms here and one term here. That's why I kept putting like k here and then k plus 1 here. Or is that you just leave it at n regardless of what term you're working with? Then you're trying to see if your property is still true at n plus 1, assuming property at n is true. I mean, this one was a pretty tough one. I actually had to like see what I was not seeing, and then I was like, oh wait, like this looked like an obvious pattern, and I was like, oh, we had to remember that this was that, and then that was the one thing. But yeah, I think this proof turned out pretty well. It's not well written, but at least like we have an idea of what we're working with here. So okay, I think wow, we took like about an hour on that one. An hour and a half actually. Oops. I try not to take too long with that, like, and that was even with ChatGPT's help, but I guess we managed to do that, so I would say that's a success. Alright, so we gotta do proof 1.14. Oh, this is a supremum proof. So I guess we're gonna have to look for definitions about supremums, and I think we have some. Yeah, I think we have some here. So let's copy this and bring it down here. And I think we need the definitions, so back into the book. Supremums are unique. Let's see, uniqueness. I think we have to get the definition of boundedness. Okay, here we go. So I don't know why it doubles up like that. Oops. I should make it smaller. I don't know if you guys can read that, but I'll just minimize it. I don't know if in English we say initialization and here, but when we talk about conduction, maybe. But then again, like, I am not well versed in mathematical literature sometimes, so sometimes I forget the actual wording of it. And plus, I haven't worked with proof by induction in a long time. I just remember the techniques. But then again, I probably haven't worked on my mathematical writing etiquette when it comes to these terms here. So it's probably just me. I'm not trying to be difficult. It's just that I'm trying to help myself visualize stuff, because like I know maybe like you're right, it's just n throughout the whole thing, but for me, I guess I had to write the terms like in like outwardly and like so I can see it. That's why I write it like this. So it's like, okay, I'm working with the first term, I'm working with the first term and the second term, and now I'm working with the k term, and now I'm working with the k plus 1 term. You know, like that was just me trying to keep track of what I was doing. But that probably might not be the mathematical etiquette thing to do when it comes to writing that. So it could be just me. Okay, no problem. I think it's because I haven't worked with sums in a long while. So like for me, it's like I forgot the etiquette of what it is to like write the sums properly. So, you know, could be that too. Let's see. Assume that A is a subset of B and both are bounded above. Prove that the supremum of A is less than the supremum of B. Ooh. Okay. So let's see. Let S be an ordered field. Okay, bounded above. Okay, so what does it mean to be bounded above? A set A is bounded above if there exists B in subset in B in S, such that X is less than or equal to B for all X in A. In this case, B is called the upper bound of A. Okay. So assume that B is a subset, A is a subset of B, and both are bounded above. Prove that the supremum of A is Sorry, I was like looking at the Discord. I saw like someone updated something. Alright, so both are bounded above. So they both have, okay, so let's see here. The least upper bound of A, if it exists, is some, okay, B naught in S, such that 1 B naught is the upper bound of A, and 2 if B is any upper bound of A, then B naught is less than or equal to B, such that B naught is also called the supremum of A and is denoted by the supremum of A. Okay. So I feel like these two definitions are gonna help us. So, proof. Assume that subset of B and both are bounded above. Okay. If that is the case, oops, no, that probably is not the right wording to put there. Since A is bounded above, then there, there exists some B in B such that X is less than or equal to B for all X in A. Thus, B is an upper bound of A. Okay. Okay. So, let's see. But B is also bounded above. But the thing of it is that where is it bounded above relative to? Is it S? Let's see. Do we have to make up another ordered field? So to we have to like rewrite this so it's like maybe we have to assume that A is a subset of B and both are bounded above. We have to are subsets of maybe we have to write let S be an ordered field first. Use A for that one. Maybe we should use like a different letter, but then again we would have too many variables, so maybe we should just forget about B so far, because they're both bounded above, so definition 2. I feel like that might help us in some way. Oops. S has the least upper bound property if given any non-empty A subset S where A is bounded above. A has an least upper bound. In other words, A supremum is Okay, so I think that helps us out a little bit. Just drag this over here. Okay. Since A is powdered off. Like right now I'm debating whether I have to start with this portion, or we should start with this one, because we have to prove this one. So that's the difficult part, is just basically figuring out which end to start with. But I feel like this one gives more definitions, so it gives, I mean, well, not definitions, but gives us more information. But also the supremums also give us like one definition to work with, so it's kind of like less information, so it's like the thing of it is that since they're both bounded above A and B, I'm like wondering if we have to actually incorporate like different variables. So like, because we know we have to show that the maximum of A, I mean the supremum of A, along with the supremum of B, is going to be like within S. But at the same time, it's like the supremum of A is going to be contained in B. So it's like a lot of stuff that is contained in one another. So it's like a box in a box in a box. That's the one thing that I'm trying to figure out exactly how can we write this without having to make it a mess. But I think we might have to save that for the next stream. At least we got one problem done though. We managed to get this by proof of induction, so my hunch was right. It's just that basically getting stuck on the basic scratch work is like the thing that kind of got me a little bit like iffy about. So maybe we have to write first term, second term, and kth term, and k plus 1 term. So that way it looks nice and organized at least. So I think we'll carry on with this one tomorrow. But it looks like it's going to be a problem that's going to be like pretty interesting, because it's like involves supremums, and this is one of the exercises that's not just said that was pretty important. So I feel as if that is going to be quite interesting, and hopefully we'll be able to complete it tomorrow, along with I think we have like 3 more problems, including this one, to do. But thanks for joining me today, guys. If you like math or physics and you just want a study stream to keep yourself productive in front of the computer, if you're watching this on Twitch, drop a follow. It's always appreciated. If you're watching this on YouTube, leave a like, comment, and subscribe. If you like math, physics, and or you just need a steady stream to keep yourself productive, please do, because there are times when I am quiet, so you get to focus on your on the stuff that you're working on. But yeah, this was really engaging to basically try to get like at least more proof muscles out of this. I'm still lacking when it comes to like writing proofs, but at the same time it's like I feel like I'm starting to get a little bit like of the muscle when it comes to like writing the proofs and actually like writing how to write them correctly. So yeah, and always remember, guys, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care, guys. Bye bye.